so before I take roll, I'm gonna show you guys a few YouTube video clips, that I was it was recommended to me, this morning by some of the morning students. So we'll go here, and this one has to do with robots, self-assembly. Okay, this is not this one here. Okay, so this is really quite interesting, and we're gonna turn on the speaker here a little bit, and go. And
you gotta click the speaker on the bottom.
Oh,
you have it.
Oh, I muted it.
Configuring robot systems. These are modular robots with the ability of changing their geometry according to task. And this is exciting because a robot designed for a single task
I really hate to bring this up, but she needs, self-assembly hair.
Exactly.
I didn't notice it the first time, and then it just kind of dawned on me. Okay, self-assembly hair.
Has a fixed architecture, and that robot will perform the single task well, but it will perform poorly on a different task in a different environment. If we do not know ahead of time what the robot will have to do and when it will have to do it, it is better to consider making modular robots that can attain whatever shape is needed for the manipulation, navigation, or sensing needs of the task.
Up until now, most other modular robotic systems use servos and motors in order to have arms and attachments that move modules into different places. However, we wanted a simpler approach that uses fewer actuators, fewer moving parts, and was easier to implement on a lot of different robots. And so the approach that we chose is to use angular momentum. And essentially what that means is there's a spinning mass that spins inside of the robot. We want the robot to move, it stops that spinning mass, which takes that motion from the mass and applies it to the robot. And a part of this that's unique is that the spinning mass is completely inside the robot, and so the robot doesn't have to be in a certain position in order for the force to be acted upon the robot. And so this allows for a lot more types of motion with only one actuator.
So there were a couple challenges when we came to design the M blocks. One was fitting everything inside. So we have a relatively small volume, and we needed to fit a brushless motor controller, a flywheel, a braking mechanism, electronics, a radio, a battery. Additionally, we faced the challenge of trying to simplify and make the design as robust as possible. So we didn't want any external moving parts, we didn't want latches, we didn't want the cubes to change their shape. We just wanted simple blocks that were able to move on their own. The magnet system in the cubes is one of its key features. So we have face magnets. There's 8 face magnets that provide some coarse alignment. And then there's these edge magnets, which are free to rotate. And the key is that when a cube starts rotating, the edge magnets actually get closer to one another. So if we start from this configuration and we break the face magnets free and start rotating, the edge magnets actually get a little bit closer due to the fact that the edge is slightly cut back or chamfered. And as a result, you form a very strong bond between cubes, which allows them to stay attached as one is rotating into a new position. It continues rotating, the face magnets provide alignment, and it snaps into place.
One other benefit of having an inertial actuator is that the cubes are able to jump, and this is a capability that very few robots have, and especially very few modular robots, because in order to jump, there's a requirement for a very high amount of energy in a very short amount of time. And most robots are optimized for control, stability, and precise motion. In our robot, we found it kind of as an accident that they're able to jump. We weren't intending to do that, but it ends up that we need enough momentum inside each cube in order to move on a lattice structure, which is what we intended, that we can also, when we apply as much energy as possible, it can jump through the air, which is pretty exciting because it also allows robots to jump on top of each other and to go places that they couldn't go if they were only moving directly on the structure.
Currently, we're sending commands to the modules with a radio. So we type commands on our computer, those are transferred over a wireless link, like your Wi-Fi system in your house, and then the cube responds to that. In the future, we envision putting the algorithms on the modules themselves so that they completely autonomously, in a distributed fashion, decide how, when, and where to move. So we want to be able to take a large group of cubes and tell them form the shape and give those instructions at a very high level, and then have the cubes decide on their own how to go about accomplishing that task.
So that's one. And then there's another one that's kind of related, but it's also, kind of in a way even more interesting. It's called swarm bot. There we go. And I think it's the second one. Oh, I don't think it's the second one. This one here. It's the same type of robot, but this one is kind of interesting in its own way. It's not self-assembly.
A recent trend in robotics is to get lots of robots working together. But parallel operation is not always enough. Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyse the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to form the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots have very different views of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground. This one, for instance. To start the selection process, the flying robot illuminates its red LEDs. To join the selection process, the robots on the ground light up in blue. In a series of elimination steps, each ground-based robot independently displays a sequence of randomly selected colours. At each step, the flying robot matches the colour of the target robot. Whenever a robot on the ground sees that its own colour doesn't match the flying robot's colour, it eliminates itself. The process continues until only the targeted robot is left. An extended version of this method allows adjacent groups of robots to be selected and then given movement and morphology formation instructions. Here, the flying robot has already targeted the 4 robots closest to the hill and instructed them to form a line morphology. Spatially targeted communication expands the potential of self-assembling systems by allowing ground-based robots to benefit from cooperation with flying robots. Any robotic platform equipped with LEDs and a standard camera can participate in spatially targeted communication. Our current focus is on bringing our research out of the laboratory and into the real world.
Of course, until the flying robot comes crashing down and the blade hits the person. This movie is called Shaving. And of course, if you really want to, kind of project, where this is all going, I can give you. I think that's where it's going. Bugs, yes. They're also replicators.
I can see that.
He's having too much fun. Don't interrupt him. Okay, so the replicators are basically self-replicating robots. So they are just kind of in a way the future of the self-replicating or the self-assembling robots. And of course, as you can see, they stand no chance against earthly, weapons. Just, really fast-moving lead, is very powerful against, any type of alien invasion. So always keep some lead at home against space invaders. Alrighty. So what do you guys think? Very cool. And what is really missing is really the software. I mean, as the guy said, these things are all controlled by a centralized command, and they don't really talk to each other much. And then that's really the problem. Okay, it's really a software issue, and also the hardware is kind of big right now. Can anyone remember how big and expensive laser printers were when they first came out? Okay, they were the size of a refrigerator and super expensive, really heavy, and not really that fast. I mean, they were faster than dot matrix printers at the time, but not exactly, how we would describe as fast by today's standard, right? So if you project, a few years down the line, if enough effort is put into these, robots in the design and implementation, you can probably find, these robots to be smaller, more agile, more intelligent, and they can potentially do more. Right now, they don't really do much. I mean, they're really just a proof of concept. But I think, that's really going to change especially once the military finds application of something, it will just accelerate the development. It just go poof like that, from going to nowhere, So I'm going to pass the roll sheet for today first, and then we'll continue to talk about things related to this class.
Have you heard of the Loon project?
The what?
The Loon project?
Mm-mm.
What they're doing is they're trying to set it up so that there's free internet for the world, and the way that they're doing it is they're putting a bunch of
Balloons?
Huh?
Balloons?
Yeah. Putting
Uh-huh.
a bunch of balloons with a bunch of technology and then that
And
communicates.
they have solar panels, so they can basically stay powered.
On the sun, on the atmosphere.
That would be
planes and
kinda
stuff,
cool.
and just communicate.
All right. So we were talking about top-down design before, and I think last time we completed the top-level algorithm already. So now it's time for us to take a closer look at the sub-algorithm. I think last time I also showed you a spreadsheet. We were trying to factor 8989 using a spreadsheet. Do you guys still kind of remember that vaguely? Okay. So what we'll do today is we'll try to write an algorithm to do it. Did we finish the algorithm or no? Okay. So we'll get started with that one, and then we'll have a little theorem to prove today. Okay. So there's a little bit of math today as well. Okay. So what we'll do is first of all, let me just kind of remind you what the spreadsheet looks like. Okay, I don't think I saved it, anywhere, but that's okay. We can always just quickly reconstruct the spreadsheet. It is very important before you write any algorithm in any programming classes that you understand how to do something yourself first. Okay, because otherwise, there's no way you can actually tell a computer how to do something. So, nope, we don't want to look at that. There we go. Okay, so we were dealing with 8989, and in each row I have the reference to just the number itself, and then we start with 2, which is the first prime number, and then we also have the remainder of 8989 divided by 2. In this case, it's called a mod operator. So we have the mod of D2, which is 8989, and also the potential factor. In this case, it is 2, and that gives us 1. Do you guys still kind of remember this step? Okay, very good. And then for each step, forward, we refer to the previous potential factor and just add 1 to it. The other 2, we can just go ahead and drag it down. So, and after this point, I can just do it really quickly, like that. Okay. By the time we get to 89, you can see that this row has a result of 0. In other words, the remainder of 8989 divided by 89 has a remainder of 0. The division has a remainder of 0, which means 89 is a factor of 8989. 89 is a prime number. So that's one of the two factors of 8989. The other number is 101. Okay, so are we still okay with this? Most of you still remember this spreadsheet? All right. So what we'll do now is we are going to take a look at the algorithm. How do we write an algorithm to do exactly that? All right. So let's go ahead and start with the question. Okay. The question is what we did. What we did was this spreadsheet here. Does it seem repetitive to you? Does it seem like we are kind of applying the same step over and over again with different values? Okay, that seemed to be the case. So that suggests the use of what type of statements? Loop. Okay, very good. So we'll go ahead and start with the concept of a loop. So we say loop, and at this point we only want to know, is the loop going to terminate? Are there any type of situations where we do not terminate? If you give me a number, a specific number, and ask me to find a prime factor of that number, and I use the method that I just described here, will we always terminate? Okay, it should always terminate. So that means we can also specify that this loop will exit when a certain condition is true. When do you think this loop terminates?
When mod is 0.
When the mod is 0. Okay, so I will just say when the remainder is 0. Okay, it's awfully vague, but that's okay. We'll clarify it later. When you're writing algorithms, or when you're starting out here with writing an algorithm, don't expect to write everything in crystal clear language in the first try. Okay, sometimes it just doesn't work out that way. If you can only work it out to this way, this particular level, it's a little bit vague, but it's okay. It is still very useful because it makes it possible to get to the next step. Okay, the next step is we'll try to make it a little bit more clear. What do you mean by a remainder? What do you need in order to have a remainder of some sort? A remainder is a product of what? What type of operation? A division. Very good. So that means the remainder of something divided by something else is 0. What am I dividing by what else? Well, the number, the dividend, is something that's given to me, right? Somebody tells me, oh, TAC, find a prime factor of 8989. So that's the number. So I would say when the remainder of a given number divided by what? How would you call 2 in this case?
Possible factor.
Possible factor? Okay, we'll just call that. Okay, by a possible factor is 0. Okay, that's fine. I mean, it's better than the first one because the first one is really vague. When we just say the remainder is 0, well, what are we talking about? The next one, we'll just use variables. So I'll just use n, be the number, be the given number. Okay, so this is the number where we'll try to find a prime factor of, and then let f be the possible factor. Okay, so what this allows us to do is we can now simplify the loop significantly, because now we can say loop, and exit when n mod f equals to 0. Because n mod f is another way to say, the remainder of n divided by f. The mod operator may look kind of strange or useless to many of us at this point, but it turns out to be a really useful operator later on, for all kinds of applications. So the mod operator does exist in most programming languages, including C++, Perl, PHP, Visual Basic, and so on. So the mod operator actually does exist. It finds the remainder of a division. Okay, so we'll call this, another stage. And at this point, it is really clear, at least to me, that in order to make the exit condition true, n mod f equals to 0, I have to change n, f, or both of them inside the loop. Because otherwise, if the condition starts off being false, it will just remain false if I don't change something. Is that making any sense? Does it make sense for me to change n? No, because n is a number that is given to me. That is the problem that I want to solve. So the only one that I need to change is f. Okay, very good. So now that we know that we are supposed to change f, how are we changing f? Which column do you think represents f in the algorithm?
C.
Column C, very good. So how do we get to the next value? We just add 1, okay? You just sequentially go to the next number. All right, so we'll go ahead and just say f gets f plus 1, like that. And we're almost done. We're almost done except for one thing. If you look at both lines that mentions f, the first access to f is a read access. In other words, on the second line, when we say f gets f plus 1, it seems like it is an assignment statement that we are changing f. But remember, in an assignment statement, it is broken up into 2 stages. The first stage is to evaluate the right-hand side, and only the second stage is storing it into a variable. So in the first stage, it is a read operation, because in the first stage, the right-hand side is simply saying, what is the current value of f? Give me that value, I'll add 1 to it, it becomes the result of the right-hand side, and then we change the left-hand side. So when you look at this entire thing, the first thing it does is to read it. The second line, or the third line here, is obviously a read operation, because all we are doing is we are using f as a divisor in a division operation, and we are not changing it at all. So that really, we now have a problem, because where do we get the initial value of f? It doesn't say. The algorithm does not specify the initial value of f. So we have to specify it. So now we copy and paste this portion here. And then we say, maybe I should initialize f to something. Okay. Now this part is the part that is, there are 2 solutions to this. The first solution, it depends on what kind of a loop you choose to use. If you choose to use a while loop, then you have to initialize f to 2, which is the first prime number. Like so. All right. If you use a repeat until loop, you have to initialize it to 1, because in the repeat or post checking loop, you perform the body of the loop at least once. So that's why by the time we get to until, f will end up with at least a value of 2 in this case. Okay. I left one thing out, which is the condition of the while loop here. What do you think this condition should spell like? Okay, go ahead.
Should be a positive number.
Should be positive or just non-zero?
Non-zero.
Yeah, we'll just call it non-zero. Okay, so we say n mod f does not equal to 0. Okay? And in truth, both of these versions of the same logic, they're both correct. Okay, there's no distinction between these 2 as far as whether they can find the solution is concerned. But one is better than the other one. Which one do you think is better? The while one, and it's because they're both 4 lines, so we are not saving any type of line numbers here. So why do you prefer the while one? Yep.
Because the while one specifies it specifies the state.
It specified the initial value of f a lot more clearly than the second one. Okay. The second one does not clearly spell out what the value of f will be when we evaluate the mod operation, because it was initialized to 1, and we are relying on the body of the loop to turn it into 2 before we finally get to the mod operation. So it's not entirely clear, at least not as clear as the first one, that we are using 2 as the first potential prime factor. And that's why I like the first version better, because it is just more clear. Okay? So are there any questions about this implementation? Yep, go ahead.
We didn't extract f within print.
Not here, because remember, this is specifying how the abstract operation is performed. Remember, find prime factor f of n. This is specifying the logic of that quote-unquote abstract operation. Yep.
With our analogy on the Excel, that would be the 89 that we got. F.
when it exits f would have a value of 89, assuming n is 89, 89.
What about the 101 that was after that?
Well, the 101 we get to it, from the higher levels of the higher level algorithm, which is going to utilize f and say n gets n divided by f. So this is a sub-algorithm of the main algorithm. This is implementing the abstract operation of find prime factor f of n is what this algorithm is doing. So it's a smaller problem, okay? But we have to solve the smaller problem as well in order to solve the bigger problem. Okay? Are there any questions at this point? Go ahead.
After f encounters its first value of 0, where n is equal to 0, how does it continue on to the next 0, given value of 0?
The next factor, you mean?
Factor,
Yeah, the higher level logic is going to do it. Remember, this logic here is only implementing find factor f of n. The higher level logic looks like this. It looks like while n is greater than 1 do, and while, and then inside we have find factor f of n, print f, and n gets n divided by f. Remember this logic here? This is what we got, on Tuesday as the overall logic. And then the abstract operation, which is the part that I only specify what it is supposed to do, but not explaining how it's going to do it, is find factor f of n. And that's what we were doing. We just specify that logic. So I broke a problem into a smaller problem.
My question was, where you get the what's called prime factors, when n is equal to 0, doesn't it exit the loop, and then it gives f another value of 2, so it doesn't seem correct.
Yeah, but exactly, if n is 0, it won't even enter this loop, because we only get into the loop when n is greater than 1. Okay, all right, excellent. Okay, so now we are going to look at this logic here, and I'm going to change the problem just a little bit, and I turn it into 101, okay? 101 is a prime number, okay? So according to the logic that we have at this point, let me show you the logic at this point here. According to this logic, the loop will keep going until f becomes what value? No, f. 101, okay? So when f becomes 101, then the remainder of 101 in n divided by 101 in f, the remainder of that is going to be 0, and that's when we'll exit the loop. And it has the correct answer, because 101 is a prime number, so a prime factor of a prime number has to be itself. It makes perfect sense, but I don't like it because it's not efficient, okay? Because if you look at this spreadsheet here, you can definitely see that it's not going to be terminating until we get to 101, and that's because the remainder is 0 at that point. What if I tell you that I really can exit at this point? In other words, as soon as I confirm 11 is not a prime factor of 101, I can exit the loop and make that conclusion and say 101 is a prime number. It is its own prime factor. Okay? Is that making any sense at all, that I can quit at 11? No, it doesn't make any sense? Okay. Right now, this algorithm will test everything until it gets to 101 and say, oh, okay, I have just found a factor because it is itself. It's 101 itself, okay? And I find that this algorithm is not exactly efficient. And I'm saying I can make this a lot more efficient by quitting when I get to a number that is either that's greater than or equal to the square root of the number. Okay? We can try another one. Okay? Give me another prime number that is less than 101. You can give me something bigger. I just have to make the table a little longer, but it's okay.
77? I don't know.
77 is not a prime number.
I don't know. I just do it.
Okay, give me a prime number. Give me something bigger. Okay, 200 and something, because I'm pretty sure we can handle up to 200 and something.
251.
251. Okay, so let's try that. 251. And according to this table, Not finding any zeros here, so it's a prime number. All right, so according to this logic, I have to keep going until we get to 251. Then we finally found a 0, okay? But what I'm claiming is, according to tech, we can stop, in this case, we can stop at here, okay? Once I test 16, which is not even a prime number, once I test that 16 is not a factor of 251, I can stop and say, hey, you know what? I know 251 is a prime number, and I can stop right there. Okay, but do you think that's a really kind of useful optimization? No? If I give you a prime number that is about 9 million, okay, using the logic that I'm claiming, it only has to test up to 3,000 or so. Okay, once it gets to the square root of the number that I'm testing, and I cannot find a prime factor, I can just quit and say, hey, this number is a prime number. That saving is phenomenal, okay? Because when you're thinking the original algorithm will have to test until 9 million something, but the alternative version only has to test until 3,000, the saving is a lot. I mean, that's like, what, 8,997,000 iterations are saved, which is a lot. Is it making any sense? Okay. Now, I want you guys to test a little theory of mine. Give me a composite number. A composite number means it is not a prime number. It is the product of two prime numbers. Okay? Is that okay? So 4 is a composite number because it's 2 times 2. 89 is a composite number because it's a product of 89 and 101. So give me a composite number, and I will say that one of the factors, at least one factor, is less than or equal to the square root of the original number. Guaranteed.
149.
Go ahead.
49.
49. Okay, that's exactly the same number that someone asked in the morning. So there's something about 49 that's kind of special. Okay, 49 stops at 7. Is 7 less than or equal to the square root of 49? Yes, it is. Okay, give me another number. Doesn't have to be a square, can be any composite number.
169?
169 is the same way. Okay, it's a square itself. So with 169, it will stop at exactly 13. Okay, so the question is 13 less than or equal to the square root of 13? It is. Okay. So I will bet you that no one in this class has the time to try to find me a counterexample to prove me wrong. Okay? Does that mean that I'm wrong? Does that mean I'm right? No. Remember the green circle? Okay? So the green circle in this case is my claim saying that if you have a composite number, at least one of the factor is less than or equal to the square root of the number. Okay? That's the green circle. Now, just because you cannot find a counterexample or throw a dart and let it land on a red dot today doesn't mean that it doesn't exist. So we better prove that before I utilize that theory in my algorithm. Yep?
How would you incorporate that square root in an algorithm like this?
I can stop way faster. I can stop earlier.
No, I'm saying, but how would you be able to would that be nested in there or like?
No. Okay, so let's just say that let's say I'm right. Okay, let's see how I can optimize the algorithm just a little bit, so that we can only go to the square root of n itself. Okay, so I can modify the algorithm. I will copy and paste it here, so I keep the original up there. Okay, I can just modify the algorithm here. If I want to, I just answered my question. Never mind. I was about to ask if I want a loop to exit early, should I use an or should I use an and? And then I typed, okay. We use an and because an and operation can turn something that was true to false, because I only need one side to be false for the entire thing to be false. Okay, so that's why an and makes sense here. Okay, but I won't answer my own question this time. What am I going to put here to basically say, if there is a factor, if n is not a prime number, okay, one of its factors has to be less than or equal to the square root. How do I make use of that fact in this algorithm? Okay, I know that there's f in here. I know there's square root of n in here. So the question is, how do I relate those two to stay in the loop? Not to get out, but to stay in the loop. Less than, okay? Less than or equal to or less than. Either one will work in this case. So less than is the one that I'm going to pick, because if f equals to square root of n, I would have kicked out by the first expression already. Because if n equals f squared, then f is a factor of n. The first one would fail, and the conjunction would have failed also, would have been false already. So less than is the one that we use. So this will significantly, improve the algorithm, because I only have to test up to the square root of the number instead of the number itself. Okay. So for large prime numbers for n, I can potentially save a lot of time. All right. But before I actually make this a part of the algorithm to basically say, woohoo, I can make this algorithm so much faster, I need to make sure that that really is the case. So I need to prove it. How many people enjoy mathematical proofs? All right, 1. And you need to sign the row sheet when you have time. Okay. So just remember to do it at the end of the class. All right, so let's try to prove that. Okay, when we prove something, the first thing we have to do is to identify what is it that I'm trying to prove. So we'll specify that really clearly first. Okay, TAC claims that given A is a positive integer greater than 1, given that B is a positive integer greater than 1, and P is defined as A times B, then, okay, so this is my conclusion. The given part is easy, okay? I'm just making some constraints and say that, okay, let's look at only integers, that are greater than 1, like A and B are both greater than 1, they're positive, they're integers, and P is simply a definition of the product of A and B, okay? Just so that we can refer to something easier. Okay, the conclusion, on the other hand, is the most important part, because the conclusion is saying A is less than or equal to the square root of P, or B is less than or equal to the square root of P. That's what I'm claiming. Okay, for any composite number, okay, that's the composite or the product of two numbers, at least one of those two numbers has to be less than or equal to the square root of the product. Am I making sense here? This is what I'm claiming, because that's what the algorithm is relying on in order to exit earlier. Are we doing okay so far? Okay, that's my claim. So what do you do when TAC makes a claim in his class?
Bet money.
Huh?
Bet money.
Bet money. Bet money. Or you can say, I don't think so, prove it, right? Okay, so that's what we'll do, is to prove that, okay? We'll prove it step by step. So how do we prove this? Well, the answer is proof by contradiction. Okay, proof by contradiction is a very powerful technique to prove something is right. Okay, despite the name, using contradiction, it is actually used to prove a theorem or a statement is true instead of false. Okay, the way it works is to say, let's say TAC was wrong to begin with. Okay, so my claim is actually incorrect. And we'll see what happens when my claim is incorrect. That's what, proof by contradiction, that's how it works. Okay, so proof by contradiction is saying, let's say TAC was wrong, and there exists a counter example. Okay, well, if there's a counter example to prove me wrong, what would be the properties of the counter example? Well, let's see here. Maybe the negation of that, right? because that's what I'm claiming. The counterexample proves me wrong, which means that is no longer true. Is that okay so far? Okay. That means, given the same assumptions and definitions, and those would be just these three, A, B, and P are still assumed and defined exactly the same way. The conclusion, which is this part here, is false. That's basically what it means when there's a counterexample to prove me wrong. Somebody could find a B, A and a B and define P as a product of those two such that my conclusion is false. What does that mean when the conclusion is false? So before we move on, I'll describe an operation. To some of you, it's not really that helpful or useful, but to some of you, especially those of you who want to get into computer engineering, this is a really useful operation. Okay, the operation goes like this. Okay, given two Boolean variable x and y, okay, I can say the negation of x or y is really saying the same thing as the negation of x and the negation of y. I'm claiming that this expression is exactly the same as the other expression here. Well, to some of you, it may make sense already. Okay, just intuitively, yeah, it makes sense. It makes perfect sense that x or y being false is the same thing as saying x is false and y is false. Okay, but to some people that may not be obvious. Okay, you need to have proof that this is actually right the whole time. Well, we can prove this by a Boolean table. A truth table. A truth table goes like this. X and y are independent variables, which means their values are independent to each other. When x is true, y can be true or false. When x is false, y can be true or false. So we have 4 possible combinations. Is that making any sense? Enumerating all the possible combinations. Yep.
Is it not x and not y, or is it not x or not y?
It is not x and not y. The operator has to be the other operator. Okay, so we'll check and see whether this makes sense or not. Okay, so for each row, when x is true and y is true, what is the negation of the conjunction of x and y? No, disjunction. Sorry. What is the? Okay, x is true, y is true. In this case, what is x or y? True or true is true. And what is not true? False. Okay, so the entire expression will give me a single value of false. Let's go to this side here. Okay, x is false. X is true. What is not true? False. And the other side, y is the same way. Y is true, not true is false. What is false and false? False. Okay, maybe that's just a lucky one. Moving on to the next one. X is true, y is false this time. What is true or false? No, wait. True or false? Is true. What is not true? False. Very good. And then we go to the other one and we ask basically the same question. X is true, so what is not true? Not true is false. Y is false, what is not false? True. What is false and true? False. Okay. Lucky shot, another one.
So are we, because we're saying it's not, so because it's true, then we're saying it's false. It's kind of like.
We plug in the values because the second row says x is true, y is false. So we plug in those values into these x and y's to get the result of the entire expression.
Right. So for instance, on the second row says x is true, y is false, and we put in because x is true or y is false, then we put in false.
Are you talking about
The second one.
This one here?
Yeah.
Well, if x is true, then not x is false. If y is false, then not y is true. Then we have false and true, which is false. False. Okay. So that's why we got the false. Okay. So we'll go ahead and finish the other two rows. This one is false. This one is false because it's really the same one as the one before, because or and conjunction and disjunction, they're both commutative. You can swap the two sides without changing the meaning. So this is really the next meaningful row. X is false, Y is false. What is false or false? False. What is not false? True. Very good. And on the other side, X is false. What is not false? True. Y is false. What is not false? True. What is true and true? True. Oh, okay. So we do have two columns that match up exactly. What does that mean? They're exactly the same. Okay? They express exactly the same thing. Cool. Hey, but why is that useful to us? Do you see this thing here? If I say, A is less than or equal to the square root of P, or B is less than or equal to the square root of P is false, doesn't that mean the negation of this is true? They mean exactly the same thing, right? Okay? This is false, so the negation of that is true. Are we seeing something similar to what we just looked at in the truth table? If you look at this expression here, doesn't that remind you of this? It has a negation on the outside and a disjunction in the inside. Well, if it does, that means I can now change it to this format. Okay, well, let's go ahead and change the format. It's not really that big of a deal. Okay, square root of P and not B is less than or equal to the square root of P is true, right? Because all I did is to plug in the transformation that I just proved a little bit earlier to the expression that I had in my contradiction. Cool. Okay, that's by itself, it's no big deal. And then we just say, I don't like to look at the negation of something that has a comparison in the inside. So I can just flip the comparison and get rid of the negation. Is that okay? I mean, all I did is to get rid of the negation and then turn the comparison around to express exactly the same thing. Is that okay? All right, no big deal. I mean, so far, everything is fairly straightforward, Okay, now I know that A is a positive integer greater than 1. I know B is a positive integer that is greater than 1. Can I square both sides of the inequality and maintain the inequality? In other words, A squared is greater than the square root of P squared. Does it work okay? Okay, so let's go ahead and do that. So we have A times A is greater than the square root of P, and then this whole thing squared. Wait, why am I wasting my time doing this? What is the square of the square root of P? P. It's just P. Okay, that's easier. And we can do the same thing about this one. All right. Are we still doing okay? Just step by step, I'm squaring both sides of the inequality. What I'm going to do next is to combine these two, okay? Because I know that A times A is greater than 1 for sure. I know B times B is greater than 1. I know P is greater than 1. I know P is greater than 1. So I can just combine the whole thing and say A times A coming from the first inequality times B coming from the second inequality is greater than P from the first inequality times P from the second inequality. Is that making any sense? Okay, well, that seems okay to me. I mean, it's all logically following. And now I can use the commutative property of multiplication and just swap the A and the B in the middle. So now it becomes A times B times A times B is greater than P times P. Okay, is that okay? Just basic algebra. Hold on a second here. What is A times B? P. It's P. Okay, so we have P times P is greater than P times P being true. Note we have a little bit of a problem here. It's a contradiction, okay? Because I'm claiming something that cannot be true being true, and that's why it is a contradiction. It is the same thing as saying false is true, which is a contradiction, okay? And contradictions in logic, in mathematics, is a very powerful technique, for proving, something. It's also a very interesting theme in movies too. I recommended the movie Dogma to my AM students to understand the power of contradiction. How many people have watched Dogma? Very few. Okay, for those of you who have not watched it, it's worth watching. It might, some people might find it offensive. In fact, the first part of the movie, when they first play, there's a big, huge, long disclaimer of, how some people may find it offensive. So, for people who are easily offended, that may not be a good movie to watch. But for people who just like George Carlin, this is an excellent movie to watch. Does anyone not know who's George Carlin?
George Carlin, he's like the funniest guy in the world.
But he's dead now, so.
Yeah, I know.
Which makes all his skits even funnier. Okay, well, so anyway, it's a contradiction. Wait, hold on a second here. Okay, we are focusing so much on the mechanical part of the proof that we are now forgetting about the big picture. What was the big picture? The big picture was assuming that I was wrong. Assuming I was wrong, then given the same definition and the same assumptions, the conclusion is false. But if the conclusion is false, it just logically follows that we have a contradiction. What exactly does that mean? That means that it is not possible that I was wrong, right? And what is the other way to say that it is not possible that I was wrong about this theorem?
You're right.
I was right. Yep, there you go. That's proof by contradiction. If you're on a computer science transfer degree track, you will take CISP 440 from Professor Fox, and in that class, you will encounter more examples of proof by contradiction, which is a really cool way of proving something is correct. Okay, I can give you another really quick example. Okay, this one is kind of funny. So let's say I have only 2 kinds of socks in my drawer. Okay, and that's actually true. So I wake up in the morning, it's dark because it's winter time, and I just need to have 1 pair of socks. And I'm the kind of person who do not like to sort my socks and put them nicely into little pairs before putting it in the drawer. I put everything into the drawer unsorted, okay? So now the question is, how many socks do I need to take? What is the minimum number of socks that I need to take out of the drawer to guarantee a pair?
3.
3. Okay, prove it. Okay, that's a minimum number, right? So you don't have to worry about 2. You just have to worry about 4. How come I do not need at least 4 socks, right? Or how come 3 socks is the minimum? So how do you prove it? 2 is easy to prove, right? Because I can pick one that is A, pick one that is B. Oh, okay, doesn't work. That's easy. What about 4 socks? How do you know 3 socks is the minimum?
So by your 4th draw, you will have at least taken out 1 of each, or 3 of one pair and then 1 of another, or something like that.
Well, it's actually easier than that. Okay, you prove it by contradiction. Okay, hold on a second here. What is the contradicting statement in this case? The contradicting statement in this case is I can draw 3 socks. I can pick 3 socks out of my drawer in the dark, and yet I do not have a pair. That contradicts the claim, right? That 3 is the minimum. Is that making any sense? Wait, hold on a second here. I pick 3 socks from my drawer, and there's no pair. Doesn't that mean that there are 3 different kinds of socks? Which contradicts the given fact that I only have 2 types?
Yeah.
There you go. Proof by contradiction.
You could also pick one of the same kind.
Then I have a pair. I have 1 pair and a half, right?
Oh, yeah, sorry.
But what I was asking is, how many socks do I need to pick out of the drawer to guarantee there's at least one pair? I can have one pair and one extra sock. That's not a problem. Yep. But that's proof by contradiction again. So you can see kind of how powerful it is. The other proof technique that is really useful, which we'll not even talk about in this class, is proof by induction. Proof by induction is really useful because you prove that a theorem or statement is true for case n, and then you establish if it is true for case n, if you can link case n to case n plus 1, then you have just proven it for any n. Okay, but there's also a base case like n equals 0 or n equals 1. So there's a base case, then you can have an induction step, and then you're done. Okay, so that's also a very useful proof technique in computer science. I'm not talking about calculus or differential equations or anything like that.
So in this process where you started with n as given, then the first thing you do is you put out the variables, and then you just kind of run it through that true or false, and then you run into this little conclusion portion here, or?
Nope.
Or we just did that just to kind of do that, or?
Oh, you mean this part here?
Yeah.
This part is here because I need to make that transformation. Because I need to make the transformation from here to basically here.
Right. So those are, because these are all of the possible, the true or false areas, all of the possible answers that we could have gotten, and then we kind of play it out.
This one here is really just proving whenever you see something in this form, you can transform that into this form without losing anything, without changing the meaning in any way. That's basically what it is, but I do want to prove it because remember, I want the proof to be really step by step and not skipping anything and not making any assumptions. And that's basically why I have to make sure that this one works first before I utilize it in my proof. Okay? Any questions about this proof? Any comments about this proof? Nobody wants to do it.
What if there was a third variable?
Sorry?
What if there was a third variable?
What if there's a third variable?
Yeah.
What do you mean by third variable? Like in here, there's a z?
Yeah.
But how do you put z into the expression? Because disjunction only has two sides.
Oh.
Yep. Now, for any expression that has 3 variables, then you have to list all 3. Then you have 8 individual cases because it is 2 to the power of 3. So that's how you can continue to work out the truth table. All right. So, okay. So that is all good. I mean, we have just proven something, but my algorithm is not quite done yet. Okay. So let's focus on the algorithm again. We'll just roll everything else off the screen so we can focus on the algorithm. Tell me again, what was the purpose of the algorithm? What was the description of the algorithm itself? To find prime factor f of n, right? The way it is it works in most cases. It's really smart with prime numbers, but it doesn't work the way it's supposed to. Can everybody see that this algorithm is now incomplete, which means the algorithm can exit, but f is not a prime factor of n. Okay, if it's not clear, it's easy. We can just go ahead and trace it and see what I mean by that. Okay, so we'll go ahead and just write the algorithm first. We'll say f gets a value of 2, while n mod f does not equal to 0, and f is less than or equal to the square root of, just less than is fine, square root of n. Do the following, f gets f plus 1, and while. Okay, so now we have the algorithm. We'll go ahead and trace it for one prime number and then for one non-prime number, for one composite number. And then we'll see why it's not working for one of those cases. I think some of you can see why it's not working already, but we'll go ahead and trace it. It doesn't take long. So we got comments, line number, we have f, we have n, and then we have the precondition here. F has an unknown value, n has to start with a given value. So let's try something with a composite number first, just to make sure it works. You guys can pick. 9 is good? Okay, so let's pick n to be 9, and then we can go ahead and trace the algorithm. All right. Okay, starting with line 1, f gets initialized to 2. Line 2 says, okay, this is a really kind of long expression, so I need to leave more space for myself. Okay, n is 9 mod f, which is dividing by 2. What is the remainder of 9 divided by 2? It's 1. 1 is different from 0 is true. Okay, let's check the second one. F is 2. Is 2 less than the square root of 9? Yeah, that's true. True and true is true, so the entire thing is true. Okay, no big deal. I mean, that's, it's a little bit long, but it's not really, quote unquote complicated in this case. We go to line 3, we add 1 to f. F goes from 2 to 3. We go back to line 2, and n mod f is different from 0 is false. Because 9 divided by 3 has a remainder of 0. 0 is different from 0 is false. But at this point, we do not do the short circuit because we have not even talked about it. So we'll go ahead and evaluate the other side anyway. We have 3 here, less than 3, which is also false. So we now have false and false. So the result is false. And we get out of the loop. And then you look at f. Is 3 a prime factor of 9? Okay, we're good. No problem. In the next trace, we'll look at a counterexample that will illustrate why the algorithm as it is not entirely correct, but it's easy to fix. So we have line number, we have the same thing, f and n. And this time we'll use a prime number, let's say 11, okay? And then f is unknown to begin with, line number is free, this is our assumption. And then we'll go through this algorithm and find out what happens. Okay, you will find that the optimization works the way it's supposed to, but the algorithm doesn't end up doing what it's supposed to. How could that be? This is line 1, f gets initialized to a value of 2, we go to line 2, n mod f, 11 divided by 2 has a remainder of 1. 1 is different from 0 is true. And then the other side is saying, f, which is 2, is less than the square root of 11. The square root of 11 is greater than 3, right? So, 2 is less than some value that is greater than 3 is definitely true, no problem. Okay, so true and true is true, so the entire expression that turns out to be true. We go to line 3, we add 1 to f, f goes from 2 to 3, we go back to line 2. So this time we are evaluating 11 divided by 3 has a remainder of what? 2, okay? 2 is different from 0 is true. Come on, true. Okay, and then the second expression has 3 being less than the square root of something that's greater than 3. Okay, that's true. Okay, so the entire thing is still true. We go to line 3 again. Now we increment to 4. We go back to line 2. N mod f is different from 0. It's still true because 11 divided by 4 has a remainder of 3. And 3 is different from 0. Is true. But what about the second one? 4 is less than the square root of 11 is false. True and false is false. We get out of the loop. And that is the end of it. Okay, we have just confirmed that 11 is a prime number, but the algorithm didn't do its job because its job is not to confirm whether 11 is prime or not. Its job is to find a prime factor of 11. Remember that? So now we come to the same conclusion that 4 is a prime factor of 11. Okay, it's not exactly doing what we wanted to do. How do we fix that? Add another statement. All right, very good. Okay, how do we add? What kind of statement are we adding? It works sometimes, it doesn't work other times. So that means the other statement only needs to execute sometimes, but not all the time. What type of statement? If is good.
If f is greater than n.
F will never be greater than n, but you're close.
To get to that, because when the f is less than the square root of n,
You got the right idea. You're just missing the square root.
Oh.
Then what do we do? How do we fix the result so that for prime numbers, the prime factor of a prime number is itself? How do we fix it? Come on. F equals n. That's it. F gets the value of n. That's it. Because for any prime number, its only prime factor is itself. That's it. That's the entire algorithm. Okay? But I look at this algorithm and I say, if I only have a little 8-bit processor running at 1 megahertz, this is going to be really, really time consuming. I don't like it at all. So, and that's because computing square root is an expensive operation compared to multiplication. Okay? So how do we change this so we don't have square root instead, we use multiplication instead? We have seen that technique already today. Square both sides in the inequality. Exactly. Okay, so we can do this optimization here and say f times f is less than n. Yep, that's it. I mean, that will speed up the algorithm considerably if your processor does not have a floating point unit to compute square root quickly. Okay, because multiplication, integer multiplication, is considered really fast on most modern architectures. But square root, on the other hand, still requires a floating point unit, which may be missing. Okay, it's not very long ago when cell phones don't have a floating point unit. I'm not sure whether they have it now or not, but before, like 2 years ago, they do not have floating point units. So square root would be an expensive operation to perform. Okay, but here TAC is going to say something even crazier. We'll say, but even multiplication is expensive because some processors that you can buy for 30 cents, they don't even have hardware multiplication. So to do multiplication requires extra time. So I only want to do addition. Is there a way to turn multiplication into just addition, but not the long way? Okay, I know you guys are thinking, oh, we can just add f to itself f times, then it becomes f squared. No, I'm talking about something a little bit faster. Okay, let me give you a hint. Okay, if I can give you the square of x, okay, and that's already computed. Okay, x squared is already computed as a number. Can you find x plus 1, the whole thing squared, using only additions? You have to think back to 8th grade or 7th grade, depending on your elementary school. Quadratic equations? No? Doesn't ring a bell? Okay, so I'm going to give you a clue here. Okay, I'm going to use the whiteboard, so it's all going to be recorded. And double check that the recording is actually still going. Yep, it is. Okay, so I'm going to say y is x squared. Okay, this is the way I spell x squared, basically x to the power of 2. Okay. So knowing y is already known and x is known, how do I compute x plus 1, the whole thing squared? Well, what exactly is it? Well, we use, okay, let's find out what it is, right? X plus 1 times x plus 1. You use the distributive property and you end up with what? X squared plus 2x plus 1. Okay, but there's still multiplication. X squared is a multiplication. But you know what? I gave you y already, so that part is taken care of. What about 2x? That's multiplication, right? But that's one multiplication that I can easily substitute with an addition. So now it becomes just 3 additions for any type of square, assuming that you know the square of the number before this one. Is that making any sense? Kind of? Okay, but that's a really big assumption. This is assuming that we know the square of x already, and then we can compute the square of x plus 1 really quickly. Does it fit our algorithm? Does our algorithm start with a particular number, and then we only need the square of the subsequent number that is incrementing only by 1? It does, because f is incrementing only by 1 in each iteration. So we could keep track of the square of f using this technique and completely eliminate the need of multiplication. Are we doing okay so far? So here comes the next question. What is the practicality of optimization at this level? I mean, it seems like it's a lot of work just to make the program go a little bit faster. What do you think?
If you're doing a million, if you're doing a million calculations, you're shaving off 0.001, kind of adds up after a million.
From experience, I can tell you it makes or break a micromouse robots program. Okay, for years, UC Davis, which I was a lecturer of, at the time, we make use of optimizations like this, and we were able to make our robots run really smoothly, accelerate really smoothly, decelerate really smoothly, and be able to kind of track its position a lot better compared to other schools. The other schools, understood, acceleration and deceleration, but they could not get rid of multiplication when they were determining, when to decelerate. So they were doing squares all the time, using, multiplication of, integers. And they ended up not having enough time to do that because we are only running 8-bit processors at 16 megahertz. Okay, so it was just not fast enough to do all the calculations. So all of the other schools, including the University of Hawaii, decided to give up acceleration and deceleration. So what happens when you're trying to spin a motor without acceleration? You go from 0 to 10 centimeters per second in an instant, right? Just like that. What do you think happens?
Brakes.
They ended up picking motors that are torquey enough to do that, because one limitation is your motor cannot do it, okay? But they did, pick motors that were able to do it. The second one would be friction, right? Traction. Well, they ended up using tires and wheels that can actually handle it. But what they did was they lost precision because it would actually skid a little bit before it establishes static friction. And because of that, because of the loss of precision, their robots could not really track their location in the maze as well anymore, and that really just broke the application because they just could not figure out their exact location in the maze, and that's why UC Davis were ahead of the University of Hawaii. I think partially is because of optimizations like that. So it is important. Okay, so sometimes it is important to understand little techniques like that. Are there any questions at this point about the fine prime factor example? No questions?
Just going back to that analogy you're talking about, you're saying that the square root will take up more memory.
No more execution time.
Or more execution time when you use square root, but is addition preferable over multiplication? You were saying, or
much. Because we are talking about 3 additions here, and here, in this case, the multiplication depends on the width of the operation. Are we talking about 16-bit multiplication or 32-bit multiplication? And that it actually ends up being a lot more time-consuming compared to just adding numbers 3 times. Yep. So it's a huge time saver in this case. And on most architectures, not an issue, but on architectures where resources is really limited, this can make or break a product. I mean, it really is as simple as that. Okay. Are there any questions? If there are no questions, we're going to move on because we are done with this top-down design topic. So topic 6 is pretty much done. I don't have a homework assignment for you yet, for this section. But we are moving on to arrays now. Okay, so we are talking about some new constructs in programming. Topic 6 is an approach. Okay, how do you look at things? How do you break a more complex problems into smaller problems so that you don't have to deal with a lot of details at any particular level? So it doesn't introduce new programming constructs, but the next topic, which is topic number 7, does. Okay, topic 7 introduces the concept of arrays. Okay. And it is very useful. I was waiting for this topic because it is a very fun topic. It has a lot of applications. And once you understand arrays, you can do a lot of stuff that was not possible, before we have arrays. So, what you need to do, since we are not going to meet until Tuesday, so over the weekend and the other 2 days, around the weekend, you can start to read this little note here about arrays. Okay, how many people already understand linear algebra, or have some background of linear algebra? An array is like a vector, okay, or matrix, depending on whether it's two-dimensional or one-dimensional. So for those people, you have a little head start already because the concept is really pretty much the same, even though the notation is different. For people who do not understand, arrays, I'll give you a 5-minute introduction, and then you can go ahead and read the notes, and then on Tuesday, we'll come back and actually talk about how to use arrays. So I'm not going to refer to any type of notation here that is specific to programming. What I'll do is instead I'll use an analogy to describe what an array is. At this point, we have variables, okay? And each variable is like a coffee mug, okay? It can contain a different level of liquid depending on how your program executes, okay? So we have, coffee mug X, we have coffee mug Y, and coffee mug W and Z, and so on and so forth, okay? So each coffee mug has its own name to identify itself and to differentiate itself from every other coffee mugs that you're using in the algorithm. It's useful to a certain extent, but it also runs into limitations. Arrays, on the other hand, is a box. An array is basically a box that has a name. Okay, so I'm going to call this one A. But inside the box, we can have, guess what? Coffee mugs. Okay, so inside this box here, let's say we have 3 coffee mugs. Like so. Except inside the box, you do not name each individual coffee mug by name anymore. Each one is now assigned a number to identify itself from all the other coffee mugs in the box. So you have coffee mug 0, coffee mug 1, coffee mug 2. So if you want to specify a particular coffee mug that is in a box, let's say we want to specify this one here, then you say this is in box A, and it is number 1 in box A. That's the notation that we use in programming. We use square brackets to indicate the number of the item inside the box. And I think the terminology actually kind of lends itself to this analogy because the square bracket looks like the box, right? And the A is the name of the box itself, and that's why it's outside of the box. And the number which identifies an item inside the box is inside the square brackets, inside the pair of square brackets. So that's a notation. Now, in the next 2.5 minutes, I can explain the significance of this notation. Why is this such a big deal? It seems like it's just a lot of extra work that has no benefits. The big deal is this. This notation here can take anything that will give you a valid number. In this case, the valid numbers are 0, 1, or 2. It doesn't have to be a constant like 0, 1, or 2. It doesn't have to be a single variable like I. It can be a long expression this long. As long as that expression gives you a value that is 0, 1, or 2, this will still specify a particular coffee mug in the box. Is that okay so far? That is what arrays is buying you, okay? It's buying you the ability to use something that can change over time to address or to specify a different coffee mug depending on the state of the other variables. It gives you basically what we call the ability to indirectly access something, okay? Which we did not have before using just variable names. And we have 1 minute and 15 seconds left. I'll let you guys a little bit early tonight because next week is going to be a heavy-duty week when we start to talk about arrays. So don't forget to read ahead of me because I can tell who has not read ahead of me. Okay, so you need to sign in because you came a little bit late. Oh, yeah, turn off the